Section 7.1, Part 1, the definite integral as net change. We're only going to do the first 2 pages here, and it is pretty much almost all review, so it should go pretty quickly and pretty painlessly. We're going to start off by reviewing what we know about linear motion, and we're going to look at example 1. The velocity of a particle moving along a number line is given by this nice linear function. V of t is 2t minus 2, and t goes from 0 to 4. And we want to find the position of the function at time t equals 4. And you're given the initial position, s of 0 equals 5. We're using s of t to denote the position function. So we know the initial position is 5. What's the position at time t equals 4? Now, there are 2 ways to solve this. One is our old way. We can find s of t completely, including finding the constant of integration, and then using it to find s of 4. So let's do that. Remember that we have the velocity function, v of t, is equal to the derivative of the position function. So that means that the position function is the antiderivative of the velocity function. So let's see, we have ds dt is equal to 2t minus 2. That means that s of t, if I anti-differentiate on the right-hand side, that's a little hard to read, let's fix that. So s of t, that function, is t squared minus 2t plus c. We find the constant of integration by using our initial position is 5 when t is 0. So 5 is equal to 0 squared minus 2 times 0 plus c. Therefore, of course, c is going to be 5. And now we have got what s of t is. S of t is t squared minus 2t plus 5. And then if I want the position, what I was looking for was the position at t equals 4. So s of 4 is going to be 4 squared minus 2 times 4 plus 5. And that's 16 minus 8 plus 5, which is 13. Okay, pretty straightforward. There is, of course, another way of doing it, and that's to use the fundamental theorem of calculus, part 2, which states that if big F is any antiderivative of little f on the closed interval a to b, then if I take the integral from a to b of little f of x dx, it's going to be antiderivative evaluated at the upper limit minus antiderivative evaluated at the lower limit. And that hopefully is absolutely engraved upon your hearts at this point. Therefore, we can say that if I have the integral, the definite integral of v of t dt from a to b, it's going to be antiderivative of v is position, so it's going to be position evaluated at the upper limit minus position at the lower limit. And remember that when we have the change in position, which is what we have here, the mathematical word for that is displacement or net change in position. All right, so let's use this. We know, therefore, that s of 4 times 4 minus s of 0 is going to be the same thing as the integral from 0 to 4 of the velocity function with respect to time. We were told that the initial position was 5. We're looking for s of 4. That's what we're looking for. That's what we were asked to find. Oops. Let's do this all on the same level, shall we? So all we need to do is to come up with the definite integral, which we can do over on the side. The velocity function was what? 2t minus 2. So if I take the definite integral from 0 to 4 of 2t minus 2 dt. Okay, remember we write the antiderivative in the square brackets. Antidifferentiate is t squared minus 2t. We don't need to bother with the c because if I put c in, when I do my subtraction, the two c's are going to cancel. Let's substitute in the upper limit first. So it's 4 squared minus 2 times 4. And all that minus, substitute in 0, I get 0 squared minus 2 times 0. All that second part is 0. So it's 16 minus 8, which is 8. So we can substitute in, all right, for the definite integral of v of t dt from 0 to 4 is going to be 8. So we now have s of 4 is equal to 5 plus 8, or once again 13. Well, both methods were pretty easy to use. Both gave us the same answer. But in fact, the second one is much more powerful. And the reason it is much more powerful is that it works. Even if we can't antidifferentiate, the velocity function analytically, because we can always find the numerical, the definite integral numerically using our calculators. So we can find the definite integral on our calculators. All right, so let's do another example. Let's look at this one. The velocity of a particle moving along a number line is given by, and here we have a velocity function, time frame 0 to 8 inclusive. This time we are given the position at time 8 is 3.2. So the position at t equals 8 is 3.2, and we want, what is its initial position? We want s of 0. We don't know what that is. Okay, so when we're looking for s of 0, we know s of 8. We're going to set up an equation. All right. If we take the integral from 0 to 8, we pick 0 to 8 because we know the position at 8 and we want the position at 0. So those are going to be our limits. The definite integral of v of t dt from 0 to 8 is going to be antiderivative or position at the upper limit minus antiderivative, which is position at the lower limit. Okay. Okay, if we go to our old method and we try and anti-differentiate analytically, I think you're going to find that it's really very tough. All right, if we have the s dt equals negative 2e to the cosine t, this doesn't lend well to substitution. We're really very stuck. So we're not going to try and anti-differentiate this analytically, but our calculators to the rescue. All right, we know how to do this, hopefully on our calculators. That definite integral turns out to be negative 22.390, and that's going to equal, they told us that s of 8 was 3.2 minus s of 0. So let's get s of 0 on the left side. It's going to be 3.2 minus negative 22.390. And we're going to get a grand answer then of 25.590, and that's going to be our initial position. Okay, third example on the next page. We've got the same particle moving on the number line with the same velocity function of 2t minus 2, which is in fact a form 2 times t minus 1, and the time frame 0 to 4. And this time we want the total distance traveled at t equals 4 if s of 0 is 5. So it's the same starting position as we had in example 1. Okay, so remember we have to be careful to notice the difference between total distance and change in position. Those will not necessarily be the same thing, and we need to pay attention to the whether I'm going always in the same direction or whether I'm changing direction. Remember, the direction is given by the sign of the velocity function. When the velocity changes sign is when you change direction. So for this function, when does it change sign? Let's set v equal to 0 to help us see that. So if we put 2t minus 2 equal to 0, we can see where we cross the x-axis. 2t equals 2. T will be equal to 1. And if we were to make a sign chart for the velocity function, all right, v of t is equal to 0 when t is 1. And then when, if you look at what we've got here, when t is bigger than 1, the velocity is positive. It's negative when you're less than 1. So we can see that we're going to change direction at t equals 1. And so I need to see what's happening in the different parts of the journey. The first part of the journey from time 0, yeah, we started at time t equals 0. When we start at 0, I'm going in the negative direction until I get to 1. So I'm going to find the displacement on that time frame, which is going to be 0 to 1 of v of t dt. This time, actually, let's not do this analytically. Let's just add this one. When velocity is negative, you are in fact going to be traveling in the negative direction. Let's graph this visually, this function. Y equals v of t. Y is 2 times t minus 1. I cross the t-axis at 1. I have a y-intercept of -2, and it's a nice straight line. And we go until time t equals 4. And if my function is v of t equals 2t minus 2, when t is 4, v is going to be 2 times 4 minus 2, which is 6. So this is a point 46. Okay, remember when we were we're going to try and find the definite integrals using area, and you remember when we did this, it was easiest to, it was good practice to write the points, the coordinates of the points on your diagram. This is 1, 0, and then of course this is 0, -2, or we can just see that off the tick marks. All right, so we're trying to find the integral from 0 to 1, and we're going to just review doing that using areas. And if you look from 0 to 1, the function lies below the x-axis, so we know we're going to have a negative integral. And let's find that area. A half base times height is going to be a half of 1 times 2, which is 1. That area, the yellow area, is 1, which means that the integral, because it's below the x-axis, I'm going the normal left to right direction, it's going to be -1. Then if I want the displacement in time interval 1 to 4, you'll see that we are now traveling after 1 to 4, we're traveling in the positive direction. So we're going in the positive direction, all right? And so as long as we're going in the same direction, I can take my integral over that. So I'm going to take the integral from 1 to 4. Okay, and I'm going to do this by area. All this is just good review. Okay, so what's that area going to be? A half. This is 4, that's 1, so this is 3. Okay, so the one leg of my right triangle is length 3. The other is 6, so a half times 3 times 6 is a half of 18, which is 9. So that green triangle has area 9, and that means that the integral from 1 to 4 of v of t dt is positive 9. It's above the x-axis, and I'm going left to right, usual direction. All right, so I travel, my displacement is -1 when I'm going in the negative direction, which means I travel 1 unit in the negative direction and then 9 units in the positive direction. And the total distance traveled is given by, we take the absolute value of -1 plus 9. So I travel 1 unit in the negative direction, 9 in the positive direction, which is 10. So the total distance is going to be 10. And if all of this looks familiar, yes, it is really just like what we did with total area. So it's just like my total area sort of problem. If I want total area, then I take the integrals separately for any areas underneath the curve, and then separately any areas above the curve, and add absolute values together. Is there another way of getting total distance? Yes. Again, this is very similar to what we did when we did total area. And that is to consider the absolute value of the function. So if I have the absolute value of v of t, remember what it looks like. It means I'm going to flip any area that's below the x-axis so that it's now above the x-axis. All right, so this is the function y is the absolute value of v of t, and I've just drawn in the vertical lines to look at the areas. All right, okay. And you can see that this area is going to be 1, this area is going to be 9. And so if I just, the total area is obtained by just taking the integral of the absolute value of v of t dt from, and I'm going from time t1 to t2. All right, remember the name we gave to the absolute value of the velocity function? We call that the speed function. All right, but you need to do that using a calculator. In order to take the definite integral of absolute value like this, you'd need your calculator. All right, so let's summarize what we've done. Displacement on a time interval is simply the change in position and happens to be the same as the definite integral of the velocity function. Notice that the displacement is not the same as distance traveled. Okay, it's equal to distance traveled only if your velocity function is positive or maybe just touching the t-axis. All right, if you are below the t-axis, then most certainly it will not, this displacement will not be the distance traveled. And then to get total distance traveled, it's going to be the displacements when traveling in the positive direction plus the absolute value of any displacements when traveling in the negative direction, like we did up here. When you're traveling in the negative direction, your displacement is going to be negative. And so I need to take the absolute value of that to get the total distance. Or if it's a calculator active problem, then you can cut to the chase and do it all in one fell swoop and just simply take the definite integral over the time period of not the velocity function but the absolute value of the velocity function. And to finish up, just one quick note. Notice if you take the definite integral of the absolute value of the velocity function, you may not get exactly the same answer as if you take the definite integral first and then the absolute values. So you need to be a little careful about how you write that. And this is it.